Okay, so let's start another problem here. Just kind of moving further down along this list. So this problem says, show that if G is a non-abelian finite group, then the order of the center is at most 1/4 the order of the group. Now, when I first looked at this problem, we have the assumption that G is non-abelian. We know that it's finite. So it's kind of hard to really get started on this with the fact that G is non-abelian, because that doesn't give us any helpful information. So I thought instead, maybe what if we did proof by contrapositive? What would that look like? So if we take the contrapositive statement of what we're trying to prove, then we are going to say if the order of the center of G is strictly bigger than 1/4 the order of G, then G is abelian. This is a bit of an easier approach when it comes to the statement here, because we can find multiple ways to show that a group is abelian rather than to start with a non-abelian group. That doesn't really give us any useful or insightful information. So let's go ahead and get started with our proof. And I want to recall a theorem that I actually have a video for. It's one of my other videos. We have shown that if G mod its center is cyclic, then G is abelian. Again, I'm not going to prove this. I already have a video of this up on my channel, but we're going to use this. To prove the statement above. So let's go ahead and suppose. Let me get my blue back. Let's suppose that the order of the center is strictly bigger than 1/4 the order of G. Now, if we just move some things around, then we have that 4 is strictly bigger than the order of G being divided by the order of the center, but this is just equal to the order of the quotient group G modded by its center. This is where this theorem that we stated up here above is really going to come help us out. So let's consider the quotient group then, and let's take a look at what happens. If we can argue that this quotient group here is cyclic, then we can prove that G is abelian. So let's consider the group G modded by its center. This group has orders. The only possible orders are strictly less than 4. So this group has order. It has to have order 3, 2, or 1. It has to have order 3, 2, or 1. Now, what do we notice about all of these numbers? Yes, they are all prime, all of which are prime. By this point, you can probably see where this proof is headed. So all of these possible orders, 3, 2, or 1, are prime. So that means that the quotient group has prime order, which of course makes it cyclic, because every group of prime order is cyclic. So making it cyclic. And again, let's recall that this quotient group being cyclic implies that G must be abelian. So G is abelian. So this is a nice little application using that highlighted theorem to show that the center of a non-abelian group cannot actually be too large. It can only be at most one-fourth the order of the group. And that completes this proof and completes this video.